I'm Anil Kumar, starting with a series on differential equations. Thanks to all my subscribers and viewers who had been asking for it for a long time. Now, it is also a good time for you to start looking into differential equations. We will move slowly and take up examples which can help you to prepare for IIT JEE and also AP calculus, right? So AP or AB calculus. In part 1, I'll discuss about what differential equations are, basic concepts. We'll talk about order, degree, type of differential equations. We'll have a worksheet on this topic, then verify general solutions, formation of differential equations. In that, we'll take up examples relating to line, parabola, circle, ellipse, sinusoidal functions, and exponential functions. We'll take up some interesting examples which can help you for IIT JEE and AP calculus. In part 2, we'll actually look into how to solve differential equations. They can be categorized into different groups. So first group is kind of geometrical solution, where we look into direction fields and Euler's method. Now this is very important for AP calculus. And then we'll look into examples with variable separation, reducible to variable separation, homogeneous differential equations, reducible to homogeneous differential equations, and then we'll take up questions from previous test papers of IIT JEE. So let's begin with that. Let me just give you an idea of what differential equations are. Now, this video is on YouTube, where students all over the world will be watching, and some of my subscribers who are actually looking into all my videos, they are in grade 10, for example. They have no idea about calculus. Therefore, I'll keep it very simple and I will introduce concepts slowly so that if they want, they can catch up and appreciate it. Okay, so let's talk about equations first. Let's say if I have a simple equation, 2x plus 4 equals to 0, then we can easily solve this equation. And when we solve, what do we get? We get 2x equals to minus 4, x is equals to minus 4 over 2, and that gives us the value of x, which is, let's say, minus 2. Now that is a linear equation, single variable. You could have equations like quadratic equations like x squared plus 2x plus, let's say, 3 equals to 0, or you could have cubic equation x cubed plus 2x squared plus something, let's say 5 equals to 0, right? So we had been working with single variable equations a lot. We had been writing them also in this form, like y equals to 2x minus, let's say 1 over x, in different forms, right? So where y is the value of this equation, where x is basically an independent variable and y is dependent on x. So we had seen gradually how equations work, and then we actually moved on to equations involving exponentials and trigonometric functions. For example, we have done equations like sine x plus cos x equals to 1, for example, right? So we also done exponential equations, for example, let us say 10, okay, something like this. So what I'm trying to tell you here is that we knew all these equations, we have worked with them, and we know how to classify them. So these equations are classified as per their order. We refer them to as polynomials, correct? Where the degrees are positive, non-negative integers, and they are defined by their degree or order, right? So we say this is a cubic equation in independent variable x, right? Now that forms a rational equation. Then we have a sinusoidal trigonometric equation, and that's an exponential equation, correct? So the equations have a name depending on what type of terms we have in them. Now a differential equation has terms like dy dx. Now dy dx is derivative of a function which is y, with y is dependent on independent variable x, right? So, but we could have an equation like this also, d2y by dx square plus dy by dx equals to 1, for example, correct? So as soon as we involve derivatives, right, in that case it becomes a differential equation, right? So just to give you an idea, we are talking now of these kinds of equations which could also be represented as y prime, that's the notation. Same equation, let me write this in different notation, let's say 1. So this is different notation. We say y double prime second derivative plus the first derivative gives you 1, right? So if we have derivatives involved in our equation, we'll call them differential equation. That's the beginning to understand what differential equation is. And now let's look into details, right? So let's define differential equations first thing. An equation containing an independent variable, dependent variable, and differential coefficients of dependent variable with respect to independent variable is called differential equation. So, okay, so might be confusing, but let me just give you an equation, then we'll talk about it, right? So we say, if I write 2 d2y by dx square plus dy by dx plus y equals 2, let us say 4. Now in this equation, what we see here is that x is independent variable, y is dependent variable, dy dx, which we say rate of change, right? Dy dx gives you dynamics to this equation. That is rate of change, and we call them differential coefficients, right? So equation containing independent variable, dependent variables, independent, and differential coefficients. So these are the differential coefficients. So normal equations which you had been working with, we had kind of x square plus x plus 5, something like that. But here the equation is in differential coefficients. Correct? Differential coefficients of dependent variable, that means dy, with respect to independent variable dx. Correct? So it is differential coefficients of dependent variable, which is y, dy, correct, with respect to independent variable, which is dx. So I hope now all the terms are very clear, right? So this is independent variable. By default we are going to take x. Dependent variable, by default we are going to take y. Differential coefficients will be dy dx, right? Where you can see differential coefficient of dependent variable, which is y, with respect to independent variable dx. Do you see that? So with respect to independent variable, let's call this as dx. Dependent variable, that we'll say dy, is it okay, is called differential equation. So differential equation will have all this, correct? So that is bare minimum. It could have more than this also, right? It could have more than this, but that is a must. So what basically is a must is at least one differential coefficient is a must. Is it okay? So even if I say, let's say, if I say dy dx equals to 0, for example, right? That is also a differential equation, right? Since it has a differential coefficient, there are two variables. X is independent, y is dependent. Perfect. So that is how we will look into differential equations. Now in differential equations, we have two types of differential equations. When we are talking about independent and dependent variables, we can, and we have very clearly said that the differential coefficients are with respect to independent variables. In ordinary differential equation, we will involve derivatives with respect to only one independent variable. So that's kind of very important. Only one independent variable. So only dx, 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 dx in all the terms. Correct? Now, the other kind, if we involve more than one, like dx, dy, dz, for example, in R3, we have three planes, anything moving here, there we could find rate of change with respect to x, y, or z, right? So in that case, we'll call them partial differential equations, right? So we have two categories. One is ordinary differential equations, the other one is partial differential equations. Now, partial differential equation involves derivatives with respect to more than one variable. For example, you could have dy, delta y, I will say, over delta x plus delta y over delta t equals to 0, for example. So here we have differentiated with respect to x and also with respect to time. Perfect. So we are not getting into this at present. We will only talk about ordinary differential equations where the derivative will be with respect to x. Correct? So those of you who are getting really, confused because of derivatives, you could think as a rate of change with respect to independent variable x. Okay? Let's move on. So let's take few examples now. Okay, here we'll talk about forms of differential equations. I may write an equation in very different forms, right? For example, there are three basic forms. Let me just get into these three first. Derivative form, differential form, and differential operator form. So derivative forms are like this: d2x, d2y over dx square plus dy dx, let's say plus y equals to 5, for example. So that kind of an equation will be in derivative form. If I write in differential form, we have kind of a shortcut to this. In that case, we'll prefer to write this equation as something like this. So that gives us the second derivative with respect to independent variable. So you really don't know what independent variable is. Sometimes it will be x, and sometimes we may take time as an independent variable, right? So we can have 2y plus sine x equals to 0. So we could have an equation like this. Well, remember, in differential equation, it is must to have differential coefficients, but all other things are possible in the equation. For example, we could have terms with sine, cosines, logarithms, and exponential functions, right? Now, some books will also use the differential form as with dots on top, right? So y double dot means second derivative, right? So like this, so we can have 3y minus y equals to 0, for example, correct? So that is also possible. We may sometimes put dots. And about these dashes, if we are finding, let's say, 10th derivative, right? So in that case, we cannot just put so many. We may write this as yn. So y10 may represent the 10th derivative. Okay, so that gives you a few ways of writing a differential equation. So that's a very convenient way. It occupies less space and time. Okay. Now, when we say differential operators, we use capital D here, right? So second derivative will be d2, for example, plus 3d1, right? Like this, we can say is equal to d, right? Something like this, where d is dy dx, correct? So that becomes in the operator form. So in our discussion, we'll be using derivative form or differential form most of the time. Is it okay? So that is how we are going to write our differential equations. So let's move on and talk further about order, degree, and type of differential equations, and then we'll take up more examples. Correct. So order of a differential equation. The order of differential equation is the order of the highest order of derivative in the equation. For example, if I have d3y over dx cube plus d2y over dx square, and let's say if I do this to the power of 3 minus dy dx plus log x, for example, equals to 0. Let us say we have some equation like this. Now in this case, clearly what you see here is that the derivative, this is the third derivative, third order. So this is the order. So here we see that the order is 3. So amongst all these derivatives which we are talking about, this is with the highest order. So that becomes the order of differential equation. Correct. Now let's talk about degree of differential equation. The degree of differential equation is the degree of the highest order derivative when it is written as a polynomial in differential coefficients. Degree may not be defined for a differential equation. Now in this particular case, the highest order is of the very first term, which is 3. Now degree is 1 here, right? So we say here the degree is 1. So in this particular case, we have written an equation which is of polynomial form. When we say polynomial form, what we're trying to say here is that all the exponents are non-negative integers. Do you see that? So polynomial forms will say exponents as non-negative integers. Is it okay? And all coefficients are either constants, they are either constants or are functions, right? So we'll define polynomial function in the next slide anyway. So basically, degree is only defined if you could write your equation in polynomial with differential coefficients, correct? So these are the differential coefficients, and this part of the equation is like a polynomial. Is it okay? Where instead of independent variable x, you have dy dx. You can think like this, right? So think like this. So you could say x is being replaced by dy dx. So this portion only, right, should act as a polynomial function. So extend all your definitions of polynomial functions to the equation where we have the differential coefficients dy dx. Is that okay? So but all other things, all other functions could be part of the equation where dy dx is not there. In that case, degree is defined, and degree is degree of the term with highest order, right? So that is an example. Now let me give you two more examples here. For example, if I write sine dy dx, sine of dy dx, let us say if I write sine of dy dx plus 5 minus d. In this particular equation, if I write sine dy dx, then it is not. So here in this particular function, even if I write, for example, d2 y by dx square, let's say, equals to 0. If I take that as my differential equation, it is a valid differential equation. However, it is not written in a polynomial form, since with dy dx you have sine function, correct? So in this particular case, we have order, which is 2, right? But degree is not defined. Correct? So it is possible that in your differential equation, degree may not be defined. Define few more terms. Then I'm going to take few more examples. We'll also talk about linear differential equations. A linear differential equation is expressed in the form p0 dny over dx to the power of n plus p1, like this, where p0, p1, these coefficients of your derivatives and q are constants or functions of independent variable x. So these are functions of independent variable x. Is it okay? They could be constants or functions of independent variable x. So if you have that case, then we call that kind of differential equation as a linear differential equation, right? So what is non-linear differential equation? The characteristics of that will be degree is more than 1, right? So that is 1. Degree could be more than 1. That is to say, if I put this term to the power of 2, the degree becomes 2, right? So if degree is more than 1, it is non-linear. Any differential coefficient has exponent more than 1. So any other differential coefficient having exponent more than 1, it is non-linear. Exponent of dependent variable is more than 1. That means the last term, y, which is dependent term. Here if I put y square, it becomes non-linear. Products containing dependent variable and its differential coefficients are present. So if I write, instead of P1, if I write y times this, it becomes non-linear. So with that, I think we have understood few terms which are related to order, degree, polynomial differential equations, right? Linear and non-linear differential equations. Now based on this, here is a worksheet for you. Okay, so you can actually pause the video, copy these questions, answer, and then look into my suggestions. So in these examples, we are trying to understand what is the order of these equations, what is their degree, whether they are linear or non-linear differential equations. Is that okay? So that is what we are going to verify. Now, order is straightforward. For every differential equation, there will be an order, right? Order is the highest differential here, right? So in this case, we can see d2y dx square plus dy dx plus y. So d2y dx square is the second derivative, and therefore the order is 2. So let's write down the order first. Now in this particular equation, the order is d3y dx cube, right? So that is the order. dy dx is lower than this, right? So the order is 3. We are not bothered about whether they have degree or not. Let's first write down the order. Here, second derivative of y, right? So that means order is 2. Second derivative of y, order is 2. Third derivative, right? So we have order as 3. So order is straightforward. When you look at differential equation, we can clearly find the order of derivative, highest order of derivative, and then get the order. Now order is the most important thing in your differential equation. It also relates to the solution. Order of 2 means that there are 2 arbitrary constants in the solution. Order of 3 means we have to do 3 times derivative of our function y to get this equation. So the function will have 3 arbitrary constants. So I'll introduce you to these constants soon. Now let's talk about degree. In the first case, highest order is of the first term, which is 2, and its power is 3. Therefore, the degree is 3. Is it okay? So we get the degree. Now, this function, is it linear or non-linear? Since the order is 2 or more, I mean, when you have exponents to these dy dx terms, then becomes non-linear. So let me write non-linear. Is it okay? Now here, it is directly difficult to figure out whether this can be written as a polynomial in derivative or not. So what we will do here is, we'll do some manipulation. So let me do the power of, this is square root, this is 1/3. So common denominator is 6. So if I do power of 6 on both the sides, then what do I get? Then I get, let me rewrite here and I'll write down the answer soon. So then what I get here is d cube y over dx cube to the power of 6 times 1 over 3 is 2, correct? Equals 2. And here if I do, I get y plus dy dx to the power of square root. Half of 6 is 3. Well, you should expand this. It will be a polynomial in dy dx, correct? This is also a polynomial in dy dx. So it is a polynomial. And if you can write differential equation in that form, you can always find the degree. Degree is the highest exponent or power for the term with highest order of derivative. So the first term here, d3y over dx cube, has degree of 2, and therefore the degree of this function is 2. Is that clear to you? You can actually pause the video, get back to this. We could actually take 6th power on both sides, eliminating those radical signs, writing it as a polynomial in dy dx. Then you can find the degree straight away reading. The degree is 2. Power of the term with highest order. Is it okay? Now let's look into the next example where we know that order is 2 but degree. To get the degree, I have to write this in terms of a polynomial function. Can I do it? Let me show you that part. That's very interesting. We have ln y second derivative plus x minus sine x. Let me write the function as let's say ln second derivative equals to sine x minus x. So I'm taking these two terms on the right side. Now if I do e to the power of all this, ln second derivative, right, equals to e to the power of sine x minus x, what do I get? I get the second derivative as equals to e to the power of sine x minus x. Now clearly this is in the polynomial form of differential equation whose order is 2 and the degree is 1, since that power is 1. So this equation has degree of 1, correct? So at times it may be misleading. You may have to do some calculations, rework as I have done to get the degree. So that's a tricky part, okay? Now let's talk about linear and nonlinear. So clearly we have something which is in y, it is linear. Do you see that? In y, because the second order and there is no power to this. So it is a linear function, correct? So it is a linear function. As far as y is concerned, there is no term with exponent of y more than 1. Now let's look into the next example, which is order 2, second derivative, square, ln y. Now if I do e to the power of something, that term becomes e to the power of second derivative. So I cannot rewrite this in a polynomial form. And therefore, we say it is not defined. So in this case, it is not defined, right? So ND means degree not defined, okay? Since I cannot write this equation in polynomial form. Perfect. Now let's look into the last example here. Clearly, third derivative and the degree, since it is written in the polynomial form, degree here is 1. It is a polynomial differential equation. Since all the terms where dy dx is concerned, they are written in polynomial form. Is that true? So that is how we understand about order, degree and type of differential equation. I hope that is absolutely clear, right? So have a good look at it. Well, you can take more examples from your book and practice. Now let's move on, and we'll now try to understand how to verify general solution for a given equation. Now let us try to understand what is the solution of differential equation and how to verify it. We have two questions here. The first one is verify y equals to a cos x plus b sin x is a solution of d2y over dx square plus y equals to 0. The second one is verify y equals to 1 plus c e to the power of t minus divided by 1 minus c e to the power of t is a solution of the derivative of y is equals to half y square minus 1. Now to verify that the given function is a solution of differential equation, what we need to do is we need to prove that left side is equal to right side. So basically we have to prove that left side is equals to right side for the given solution, right? For the given solution. So that is what we have to do. So let's do it. So let's do question number 1 now. We have y equals to a cos x plus b sin x. Second derivative we need to figure out. So what is the first derivative? First derivative is cos x, derivative is minus sin x. So I could write this as minus a sin x plus b cosine x. And the second derivative is derivative of this, which gives us minus a cos x, and that is minus b sin x, correct? So if I substitute this second derivative there with y, what do I get? Well, it's very clear. You could also write here minus a cos x minus sin bx. If I take minus common, what do I get? I get a cos x plus b sin x. Now what is this term? A cos x plus b sin x is y, right? So I could also write this as minus y, right? Now if I take it on the left side, what do I get? Second derivative plus y is indeed equal to 0. So that is a solution of the differential equation given to us, d2y by dx squared plus y equals to 0. Do you get it? So in a way, we have shown that this is a solution, correct? So if I substitute, some of you, what you can do now is very clear. You could substitute this second derivative there, right? So the equation was d2y over dx squared plus y equals to 0. So if I substitute here the value of y, which is, or I could substitute d2y as minus y. I could write this as minus y plus y. We know that is equals to 0, so we know 0 equals to 0. Anyway, so what I have shown you here is also a technique of finding solution or finding a differential equation for a given function, right? So we could use this technique also to find the differential equation. Now that particular function becomes the solution of a differential equation. So you should remember one thing, that always a solution of a differential equation is a function, not a point. So it represents the whole family of curves represented by this differential equation. A and B are called arbitrary constants. So here, let me introduce the term that we have two constants, A and B, and these are called arbitrary constants or parameters. By varying A and B, we can have different curves related to the family of the given function, correct? So that is how we could actually prove it. Now let's do the second question, which is, let's verify the second part now. Here we are given that y is equals to 1 plus c e to the power of t. Derivative is with respect to time. 1 minus c e to the power of t is in the denominator, is a solution of this function, correct? So we can begin with the given function, which is y equals to 1 plus c e to the power of t over 1 minus c e to the power of t. Taking derivative, we get y dash equals to, let's apply the quotient rule here, which is 1 minus c e to the power of t whole square in the denominator. Derivative of this function is c e to the power of t times 1 minus c e to the power of t, take away. Derivative of the denominator is minus c e to the power of t times 1 plus c e to the power of t, correct? So we can simplify the numerator. Let's first expand it. So we get c e to the power of t minus, that gives us c square, or okay, anyway, that gives us c square e to the power of t times e to the power of t will give 2t, right? Minus and minus becomes plus, so we get plus c e to the power of t, and then with the second term, minus and minus is plus, so plus c square e to the power of 2t over 1 minus c e to the power of t whole square, right? Now let's combine the like terms, which is twice this, and that cancels out. C square e to the power of 2t cancels out, so we have 2 times c e to the power of t over 1 minus c e to the power of t whole square, right? So that becomes the derivative for the given term, right? So it is 2c e to the power of t over all this. Now, if I substitute this, then what happens? That's what we have to check, right? So this is my left side. Is it okay? On the right side, let's call this as the left side. Now, let's do the right side, which is half of y square minus 1. Half of y square minus 1, right? So the right side is basically equals to half of y square, means all this square, right? So we have half of, let's say, 1 plus c e to the power of t over 1 minus c e to the power of t whole square minus 1. Is it okay? So let's do that part. So we have, so that becomes a common denominator, which is 1 minus c e to the power of t whole square. When you open this up, we get 1 plus c e to the power of t whole square, right? Minus, that gets multiplied here, right? So 1 minus c e to the power of t whole square, correct? So we get that. Now we can actually expand this. So we get half of, expanding the numerator, which is a plus b whole square, we get 1 plus 2 times c e to the power of t plus the square of this, which is c square e to the power of 2t. Then we get minus of, let's put all this in brackets, 1 plus 1 minus 2 times c e to the power of t plus square of all this, which is c square e to the power of 2t. Is it okay? Over 1 minus c e to the power of t whole square. Now clearly in the numerator, you can see that some terms will cancel out. So let's see which ones cancel out. So 1 and minus 1 cancels out. This is plus and this is minus. Minus minus becomes plus, so that gets added. The last term, third term, cancels out. So what we get here is 2 times 2 is 4. So we get 4 c e to the power of t over 1 minus c e to the power of t whole square, correct? So this is equals to half, and that cancels out. So we get 2c e to the power of t over 1 minus c e to the power of t whole square, correct? So that is the right side, if you see that, correct? So we found what is the right side, which is equal to, and what is the left side, the derivative. Is that okay? So as you can compare now, so this right side is same as the left side. So since left side is equals to right side, we know it is a solution. So therefore, solution is correct. Correct. So that is how you can actually verify if the given function is a solution for a differential equation or not, right? So I hope the steps are absolutely clear. We found derivative of the given function, and we also expanded the right side and simplified, and both sides we get the same term. That means left side is equals to right side, and the solution given to us is perfectly fine. Let's move forward. Now we will take up many examples in which we will learn how to form differential equations from given functions. So we have a lot of examples here, correct? You can actually pause the video, copy all of them, and then see how to solve them. So the question here is, form differential equations representing family of curves. So one by one, we'll do each one of them. Now in this particular part, I would like to highlight few things. Whenever we are looking into functions and we want to find differential equations, then looking into functions, we know the order of differential equation. How? By checking number of arbitrary constants. The whole idea of writing differential equation is to get an equation which could represent the family of curves defined by the function, right? So I think that's a very critical term here. When we say representing family of curves, so this particular equation actually does not represent the complete family. When we say y equals to mx plus b, depending on the values of m and b, we get different lines. If I eliminate m and eliminate b, then I get an equation which represents the whole family, correct? So the idea will be somehow eliminate arbitrary constants. So this is going to be our strategy. Now, how do we do it? How do we eliminate? So as you know, derivative of a constant is 0. So we eliminate by repeated derivatives. That is how we eliminate. How many times do you have to find derivatives? It only depends on number of arbitrary constants. So that is dependent on number of arbitrary constants, which we also refer to as parameters. So sometimes I'll use the term parameters. So what parameters we have in the first equation? M and B. So let's define the parameters and then we'll move on. So here the parameters are M and B. Here we have only one parameter A. In this case we have parameters A and B. In this case the parameters are A and B. In this case the parameters are only K. Whether you write it in square root or any power, it is just K, right? Here we have two parameters A and B. In this case the parameters are A and R. So what you notice here is that orders, let me write down here order of the differential equation. We expect order of 2 here, order of 1 here, 2 here, 2 here, 1 here, 2 here, and 2 here. That is to say that in two derivatives, we should be eliminating the arbitrary constants and getting differential equation. So that is a must. You cannot differentiate it 3 times if there are 2 arbitrary constants. So that is kind of a rule, right? So keeping that in mind, let's now begin solving these equations one by one, right? So let's begin with the very first one, which is form differential equation representing family of lines. So what we have here is y equals to mx plus b. So if we draw a line, we know that for this particular line, b is the y-intercept and m is the slope, right? So depending on different values of m, for example, let's say if we keep b constant, m different, we could draw these kinds of lines. Is that okay? If we change b, for example, if we change b for different slopes, we could get lines like this. So all different lines we have to represent by one equation, and that is the differential equation which we are looking forward to. Correct? Now let's revise here. We have two parameters. So that means we have to do order of differential equation is 2, right? So let's differentiate this equation twice and in the process eliminate both these arbitrary constants, right? So let's begin. So if I do it once, that is dy dx, what do I get? The derivative will be m, that becomes 0. Is it okay? Now second derivative, if I do d2y over dx square, we get 0. So now we have arrived at a differential equation where there are no parameters. So that becomes a solution. Therefore, so the differential equation representing lines is d2y over dx square equals to 0. So it is like this. So first example is very simple. Let's move on to the next example now. You can actually pause the video, copy the question, answer, and then look into my suggestions. Now here the question is, form differential equations representing family of parabolas having vertex at origin and axis along the positive x-axis, correct? So at times, direct equation may not be given to you, right? So if you may get something like this statement. What are we trying to figure out? We're looking at this horizontal parabola which opens on the right side where the vertex is at the origin O, correct? And the axis is along the positive x-axis. That's what we're looking for. And standard equation of this curve is y square equals to 4ax, right? Now in this, look for parameters. How many parameters do we have? Only one, a, right? So the order of the differential equation will be how much? 1. In one differentiation, we have to eliminate a. That is what we're trying to see. Is it okay? So let's do it. So what we have here is y square equals to 4ax. So if I differentiate with respect to x, that is the independent variable, I get 2y dy dx equals to, this was x, right? So equals to 4a. Perfect. So we get our equation. Well, now what we can do is, we can substitute the value of 4a in there. Do you see that? This is also 4ax. If I do that, what do I get? I get y square equals to, substituting 4a as 2y dy dx times x. Does make sense to you, right? Now we can rearrange, bringing it to the right side, for example. So we get 2y x dy dx minus y square equals to 0. So that becomes our equation, differential equation, which represents all such parabolas whose vertex is at origin and axis is along positive x-axis. Is that clear to you, right? So these two were very simple examples, and now we'll take up more intricate ones. The question here is, form differential equation representing family of sinusoidal curves y equals to a sine x plus b. Now again, how many parameters we have? We have two parameters, a and b, right? So their number is 2. So that means we are looking for order 2 differential equation, right? So that means we are going to differentiate the given equation twice. So we have y equals to a sine x plus b. First derivative of this equation is, so sine derivative is cosine, so we get a cos of x plus b times derivative of inside function, which is 1. So we get the same thing. Now the second derivative is, cos derivative is negative sine, so we get minus a sine of x plus b. Now, minus a sine of x plus b can be written as y. And so we get our equation as y double prime minus y equals to 0. So that becomes the differential equation, and as you can see, it is of order 2, right? So it is of order 2, degree 1, which represents the given family of curves. Do you see that? So that is how we are going to solve it. So I hope it's not very difficult, right? You need to review some differential equations, derivatives concepts. That is all. Now let's look into next example, where we have to form differential equation representing family of exponential curves. Y equals to a e to the power of x plus b. Now again, we have two parameters, right? We have two parameters here. And these two parameters are a and b. That means we have to find second derivative. In that process, we should be in a position to eliminate it, right? So let's begin. The first derivative will be a e to the power of x plus 0. So we have eliminated b in the first shot. Now how do I eliminate a? Now that is kind of tricky. If I find the second derivative, I get a term with a, right? So this is here. This is where you need to use some techniques to eliminate a. So what I will do here is I'll rearrange this equation. Keeping constant on the right side, I could write this as 1 over e to the power of x times first derivative equals to a, correct? Which is as good as writing e to the power of minus x times first derivative of y as equals to a. Now if I differentiate with respect to x, I eliminate a. Do you see that? Correct? So we'll apply the product rule here and differentiate. So derivative of the first part will be minus e to the power of minus x times y dash plus. Now this time we'll write derivative of the second part, e to the power of minus x, and derivative for y dash is y double dash, correct? Is equal to 0. Do you get it? So we get our equation in which we have eliminated a. So now we have a differential equation from which we have eliminated both the parameters a and b. Perfect. So you could write this as, if I take e to the power of minus x common, what do I get? E to the power of minus x common. I get second derivative, take away the first derivative, equals to 0, right? So we can actually divide by e to the power of x and then write down as second derivative minus first derivative equals to 0. So that becomes the differential equation, which is the solution of the given equation, right? So you could also write this as the second derivative equals to the first derivative. Either way, both are good enough forms. Is it okay? You could always divide by e to the power of minus x since it is non-zero, right? Why could we divide it? It's important to understand e to the power of x minus x is non-zero. And therefore you could divide it, right? And get this particular equation. So I hope the steps are very clear. And a critical step here is rearrange. Since you know that in the second derivative, you have to eliminate both the parameters, correct? So I hope that is a very important exercise, and that gives you insight to how you should be solving more intricate questions where a function is to be represented by a differential equation, correct? So let's move on, take some more examples. Now here is a very interesting question. We need to form equation representing family of curves represented by the equation y equals to 2k x plus square root k. So we are given the equation y is equals to 2k within brackets x plus square root of k. Now first thing, how many parameters are there? There's only one parameter k, do you understand? So that means the order is going to be, order of differential equation is going to be 1. And that means we have to only differentiate this equation once to get our answer. Perfect? That is what it means. So let's find the derivative of this equation. So we get y prime as 2k times x, that is a constant term, so we get 2k. Okay? That's what we get. Now from here we can rearrange and write k as half of y dash. Right? That becomes the value of k. Replacing this value k here in the equation gives us the differential equation. Is it okay? So y equals to, we'll replace k, we get 2 times y prime over 2 within bracket x plus square root of y prime over 2. Do you get the idea, right? So that becomes your differential equation. Now here we need to simplify this a bit, so we could do that. So what we get here is y equals to, when you open this bracket, we get x times y prime plus we get y prime times square root of y prime over 2. Correct? So that becomes your differential equation, which is a solution of the given situation, right? So you could always rearrange it and write down the answer. So what we can do here is we can just rearrange and write this as 0 equals to x times y prime plus that becomes 1 over square root 2 y to the power of half y prime to the power of half plus 1, which is 3 over 2 minus y. Correct. So that represents the differential equation for the given function. Okay, so let's continue and do the next one. We are almost at the end, few more examples to go. The question here is, form the differential equation representing family of ellipse having foci on x-axis and center at the origin. So the equation for such an ellipse is x square over a square plus y square over b square, right? So we're looking for all the ellipse which could be represented in this fashion, correct? So depending on the parameters a and b, they will be kind of like that, centered at the origin. So here clearly we have two parameters, and so we are looking for second order differential equation as our differential equation representing all the family of these ellipses, right? So let's find the derivatives on both sides. Let's do differentiate with respect to independent variable x. So we get here 2x over a square plus we get here 2y dy dx over b square equals to 0. So in the first step, we have eliminated the right side. Now we have to rearrange to, because somehow in the second derivative we should eliminate both these parameters, right? So how can we do it? So let's rearrange it. So what we will do now is bring the terms. Let's see how to do it. So we'll actually write down the derivative term on the right side. We can actually just cancel 2's. So we can write this as y dash over b square equals to, taking it to the right side, minus x over a square. We cancel 2's. And now we'll kind of cross multiply. So if you cross multiply, you get y prime over x equal to b square over a square. Do you see that? So by doing so, we have written it as a product form here and a constant on this side. So if I differentiate now, what will happen? I'll get 0 on the right side, and here I'll apply the product rule, correct? So think like this. We have two functions here. Do you see that? So we have two functions here. And if you apply the product rule and differentiate with respect to x, we can eliminate both the parameters. That is what we are going to do now, right? So what we get here is derivative of this term, that is y over x derivative times y prime plus y over x times derivative of this function, which makes it second derivative, equals to 0. So as you can see, we have already got a differential equation where both the parameters or arbitrary constants have been eliminated. So this differential equation represents all the family of ellipses which are centered at the origin. Correct? So let's find this derivative. It is, now we can apply the quotient rule. So we have x squared. So y derivative times x minus y times x derivative times y derivative plus we have y over x times second derivative of y equals to 0. I hope you are finding this series interesting. We are almost at the end. 3 more equations to work with. Form the differential equation representing family of ellipses this time, given foci on the x-axis and center at the origin. So what we're trying to say here is that we have all these ellipses with center here. Correct? So as we change the value of a and b, we get different ellipses, right? That's what it is. So in this case, we have two parameters. It is important to figure out how many parameters so that we know what kind of result we are going to end with. So we are going to end with second order differential equations. So be clear in your mind that in two derivatives, you have to isolate x and y or derivatives and eliminate both a and b, the arbitrary parameters, correct? So first step is differentiate with respect to independent variable x. What do you get? So here we get 2x over a square plus 2y dy dx, let me write it as y prime over b square equals to 0. Now we can rearrange. We can write 2y y prime over b square equals to minus 2x over a square. Cancel 2's, bring down x and get the constants together. The idea is we have one more time to take derivative, but we should eliminate both these arbitrary constants. How can we do it? We have to get them together, right? So this is a very important step. So at this point, we are cancelling these 2's and rewriting our expression or equation as minus b square over a square. You get an idea. As soon as you do this, I know now if I differentiate with respect to x, what will I do? I'll eliminate the right hand side. Perfect. That's the whole idea. So here we can apply the quotient rule or product rule. So first let me rewrite this so that it becomes slightly simpler for you to understand. So I'm rewriting this as minus b square over a square, correct? Now we'll differentiate with respect to x on both the sides. So we'll apply the product rule, right? So we have derivative of this terms times the second term plus first term times derivative of the second term equals to derivative on the right, constant, 0. Perfect. Now let's find what is the derivative of this. we can apply the quotient rule. So you should be good at least rules of differentiation, right? I'm not asking for much, just basic rules. If you know that, you can do this particular series. So here x square in the denominator, then we get y prime x minus derivative of x, which is 1, times y, times, we already have this y dash, plus we have y over x, y double prime, second derivative equals to 0. So at this stage, we only expanded this part, derivative, right, of y over x, applying the quotient rule. Is that clear? Now, let me multiply everything by x squared. So we get y prime x minus y times y prime plus, if I multiply by x squared, I get y times x, and here double prime equals to 0. Correct? So we kind of got rid of fractions. We can expand this. So we get x y prime square minus y prime plus x y double prime equals to 0. So let's write with the highest order first. So we get xy times y double prime minus, so here we have this derivative. Let me write this as x y prime square minus y times y prime equals to 0. So that becomes a differential equation which represents the family of ellipse whose center is at the origin, correct? With two parameters a and b, right? So I hope that's absolutely clear. Let's move forward and take up the next question. The question here is, form differential equation representing circles centered on the x-axis. That means what we are looking for is some circles which are kind of like this, right? So kind of like this. Centered on the x-axis means that is the center. Let's say this point is A0, right? With different R values. Clearly, we have different R values. Is it okay? R values are different. So that means we have two parameters. We are expecting second order ordinary differential equation, correct? We are working with ordinary differential equations, differentiating them with respect to the independent variable x all the time. So let's do it. So if I find the first derivative, so let's differentiate with respect to x. What do you get? Both sides. So we get 2 times x minus a to the power of 1, okay, derivative of x is 1, plus 2 times y, derivative of y prime equals to 0. Okay. Now we have one more chance to go. We can definitely eliminate a. In the first derivative, we eliminated r. So now we get derivative of this is 2, right? That is 2x, derivative is 2, 2a minus 0. Now here we'll apply the product rule. So 2 times y derivative times y plus 2y times derivative of this, which is second derivative. Okay, now we could take 2 as a common factor, write this as 1 plus y prime times y prime plus y times y double prime equals to 0. Or we could say 1 plus, this is square, right? Plus y times second derivative equals to 0. Or rearrange, it's good to write this term as first. So y times second derivative plus first derivative square plus 1 equals to 0. So as expected, we get order 2, right? Differential equation. And what is the degree? Degree is 1, right? Since exponent of second derivative is 1, correct? So those are all the questions. Now we have a small test for you. We are going to end this video with a test question. We have two questions here to answer. I'd like you to pause the video, answer these questions, and then look into my suggestion. The first question is y plus e to the power of x plus dy dx equals to half integral y dx a linear differential equation? Determine its order and degree. Question number 2. Form the differential equation representing all non-horizontal lines in a plane. So pause your video, answer these questions, and then look into my suggestion. Question number 1. Y plus e to the power of x plus dy dx equals to half integral y dx. What we can do is we can differentiate with respect to x both sides. So what do we get? We get dy dx plus derivative of e to the power of x is e to the power of x plus derivative is second derivative of this plus half times derivative of integral y dx is y. Equals to, equals to. So we get our equation here, right? So the equation is, kind of like this. Let's multiply or bring them together. So I'm just rewriting this. We have dy dx plus e to the power of x plus d2y dx square, equals to half y. Perfect. Now, is that a differential equation? The answer is, of course, yes. So the answer is yes. And what is the order? Order is 2, as you can see. And degree, the exponent is 1. Done. The next question here is, form the differential equation representing all non-horizontal lines. Okay, so what we are trying to say here is that we will consider all kinds of lines. We'll consider all kinds of lines, even vertical, but we are not going to consider any horizontal line. So these are to be eliminated. Equation of a horizontal line is normally y equals to k, correct? Well, in general, we can write an equation ax plus by equals to 1. It represents lines in a plane. Is it okay? Now, when we say non-horizontal, that means that we are not including these horizontal lines. So we say non-horizontal means not horizontal. We are including the vertical lines. How do you write equation of a vertical line? Vertical line equation is x equals to something. Is that okay? So that gives you the equation of the vertical line. So when we are talking about non-horizontal lines, in that case, B is so whenever you're talking about non-horizontal line, in that case, B can be equal to 0, but A is not equal to 0. Do you understand? That is very important. Since x equals to something represents a vertical line. Perfect. Now, taking that into consideration, you now analyze the equation. Ax plus by equals to 1. How should we differentiate to eliminate these two parameters? So we have two parameters here, correct? So we have two parameters. We are expecting second order differential equation. Perfect. So what we will do here is we are going to differentiate with respect to y, and that makes this question very special, and it could be asked in tests like IIT JEE. So this is a very important question. So let's differentiate with respect to y. Then what do we get? So we get a times dx dy plus b equals to 0. Do you get an idea? Now we need to differentiate a second time, since there are two arguments, right? Or two parameters or two arbitrary constants. So let's rearrange. We can say dx dy equals to minus b divided by a. Now if I differentiate, I eliminate both these arbitrary constants. So we get d2x over dy square equals to 0. Now since a is not equal to 0, we can actually divide by a. No problems, correct? So what you get here is d2x over dy square equals to 0, and this represents your equation for the family of curves we're discussing, correct? So I hope that is very clear, absolutely clear. With this, we complete our part 1 of differential equations. I hope you have understood what differential equations are, and their solutions really mean a set of functions, a family of functions, not just points. That's very important. And if we are given a function and we have to write its differential equation, then the process is basically to identify how many parameters are there or arbitrary constants. Those number of parameters give us the liberty to differentiate the equation those many times. So we get a differential equation of that order, which will represent the whole family of curves. So in differential equations, we are representing the whole family of curves with the help of an equation which is in terms of dy dx. So I hope you find it useful and interesting. Feel free to share your comments and views, and if you like and subscribe, that'll be excellent. Thank you and all the best.